So, welcome friends. Today's topic is Deterministic Finite Automata, DFA. So, today we are going to start with DFA, which is first type of finite automata. And in this lecture, we will see the mathematical definition of DFA. Then we will discuss one example, and I will represent that example with the set in set form and both graph form. So I'm starting with the mathematical definition of DFA. So as I told you, deterministic finite automata or finite automata are mathematical model to create some machine or to solve some problems, right? And then I will define it mathematically. See, if I define or if I call this DFA as a machine or deterministic finite state machine, so that machine I will represent with M. And as I told you also that the all FAs are defined in terms of component, and these components sometimes called as tuples. These components are sometimes called as tuples. Generally, tuples is called for all component of finite automata. Now, as I told you, like I will represent that DFSM as M, so it is 5 component or 5 tuple machine. So DFA is 5 tuple machine. DFA is 5 tuple machine. Now, what these tuples are? So first is capital Q. Capital Q is basically capital Q is all set of all possible states of machine. All possible state states of machine. All possible states of machine or DFA, or you can say not DFA, FA, right? Then next tuple is sigma. And that sigma is basically a set of input symbols. Set of input symbols. Set of input symbols. Then third component is delta. Delta is a very important function, that is set of, or you set of transition rule. Set of transition rules. How machine is changing one state to another state, that the rules for it are defined within this set. So transition rule, set of transition rule, or you can call it, or we can call it transition function. Transition function. And transition function, I will separately discuss this also again in detail. So first let me introduce all component first, then we will start discussing all component in very much detail, right? So now next component is Q0. Q0 is basically, it is not a set. Q0 is representing single state that is known as initial state of the machine. Initial state of the machine. Initial state. It is not set. It is not set. Now next component is F. F. Now again this is one more set is there. F. F is set of all final states. As we discussed in previous lecture, like there may be one or more final states in single machine. So that will be a set. Sorry, states. So these are 5 different component of DFA, and we are representing them with some particular name. These are the standard name that we use to represent DFA. So capital Q is the set of all possible states, of the machine. And as I told you that it is also known as finite state machine, as the number of states in any finite automata are finite. So this set would be a finite set of all possible states of machine. Then second is sigma. Sigma is set of all input symbols that machine accepts. So that particular, or you can say alphabets of particular language, right? Now, let me discuss fourth and fifth first. Then we will start discussing third component in very much detail. Now, fourth component is, as I told you, this is not a set. This is single state, which is known as initial state, whatever initial state is, we can represent with it with q0, or whatever name we assign to initial state, we can replace this q0 with this particular name. Now the next component is f, which is set of all final states of the machine, so that is again a set. Now you can see, my friends, out of these five components, or out of these five tuples, all except q0, all tuples are set. So if these are set, then there may be more than one possible states, more than one input symbol, more than one transition rule, or more than one final state. Only the initial state will be single state, because any machine or any finite automata can be in single state at a time. So initial state would always be single state. Now, what is initial state? Without giving any input, if in whatever state machine is, that will be known as initial state of the machine. So that is represented as Q0. So I hope, friends, it is very much clear. Now I will discuss what one example of DFA, and then I will represent this example DFA in set form and graphical form. Both form I will discuss. I hope it is clear to all of you. So now I will discuss one example. So friends, we will create a DFA accepting all strings of 0, 1 and A and B ending with A. All strings of A and B ending with A. So see friends, so what this is like a set. Now this language, if I call this particular set as language, then this language will have all strings of A and B ending with A. That means what would be the minimum string? Suppose any string epsilon is one of the string you can consider with zero length. The length of epsilon is zero. Length of epsilon is zero. Length zero. Epsilon. So epsilon is also considered as a string of A and B. Any string of A and B, then you have to consider epsilon also. So in that way, what will be the minimum shortest string of this language? What would be the shortest string of this language? That is A. Why? It must end with A. So shortest string would be A. And before that, any string of A and B is possible. So it may be zero length also. So if we single character, or the shortest string of this language would be this A. Now, any language with any string with the length of 2, so it may be and aa and ba, because the condition is string must end with A. So now three strings are there: aaa, then aba, then BAA. Now I'm removing it. So BAA and BBA. So these are three length strings up. And now so this particular language is representing language with an infinite number of strings. Any string of you can make for A and B. Now we need to create this machine. So I will first start with graphical representation. So that would be easier to understand. So whenever you are asked to create a machine for any language, so see first the shortest string of that machine and create machine for shortest string. So we have to accept single A. We have to accept single A. So that would be that is suppose your initial state, and I'm writing its name as Q1. I am writing its name as Q1, and now after accepting A, single A, it will reach to Q2, which would be your final state. Which would be your final state. So, in that way, you can see that particular string would be accepted by this machine. But this is the shortest string. What about this? What about this? What about all the many infinite number of strings? So, you can see, friends, once you get A, that must be and last character of the string, right? So before A, you can have any combination of A and B, right? So suppose if in initial state you get A, then you reach here, then you reach here. But if you get B, then you must stay at this particular this particular this particular state. Now at this particular state, in the initial state, we have considered both symbols A and B. If we are getting A, then we will move to Q2, and if we are getting B, we will remain in Q1. Right? Now we have considered all the input symbols for this state. Now we have to consider both the input symbol for this state also. Now suppose we have already got one A here. Now if again we get A, then we can stay on this state only, because it is again ending with A, so we can stay on this state only. But in Q2, if we are getting B, then we should move to Q1 again. Then we should move to Q1 again, so that it will not end with B. So now, if you give any string of this set, you will see that at the end of a string, this will be in final state. See, if I tell you to create one string for this language, so I can create A. This string belongs to this language because it is ending with A, and it is having only two symbols, B and A. Both symbols are there, only two symbols are there, and string is ending with A. So this is the valid string for this particular language. Now let's see whether this machine is accepting this string or not. So you can see initially we are at Q1 and we are reading A. So we will move to Q2. We will move to Q2. So now after reading this symbol, we are on Q2. Now at Q2, we are at Q2 and we are getting B. So if we are getting B at Q2, so we are again going to Q1. So after reading this symbol, we will move to Q1. Initially we are at Q1. After reading this symbol, we will move to Q2. After reading this symbol, we will again move to Q1. Now, after reading this symbol, we are at Q1 and we are getting A. So we are at Q1, we are getting A. So we will again move to Q2. Then after getting B on Q2, we will move to Q1 again. So we will move to Q1, and on Q1 again we are getting A. So we will move to Q2. Q2. So this is the end of string. And now after reading last symbol, we are at Q2. We are at Q2, which is one of the final state of the machine. That means this string is accepted. This string is accepted. Right? I hope this would be very much clear. Now I will take one example of a string that is not part of that language. So I will see. Now, I will take one more example string here, which is not a part of this language. So I can have A, B, 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 this language. So this string a part of this language? No, because it is not ending with B. Sorry, A. It is ending with B. So let's see whether this machine is accepting that this string or not. So you can see, check. Initially we are at Q1. So after reading A, we will move to Q2. After reading B, this symbol, we will move to Q1 again. And after and Q1, we are getting B, so we will stay in Q1. So after reading this, we will stay in Q1. Again, we are getting B, so again we will stay here in Q1. Now, this is the last character of string. Now, after reading last character, we are in Q1, which is not a final state, That means this string is not accepted by the machine, and this is accepted. So, my dear friends, when you are creating one machine, so we need to check in both ways. Like for any valid string of this language, for any valid string of language must be accepted by this machine, whatever you are creating. Now we need to check in other way also, like any invalid string of the language must not be accepted by this machine. So in we need to check in both ways, right? So this is the machine for accepting all strings of A and B ending with B, all strings of A and B ending with B. So now I hope this would be very much clear to all of you how we can create a machine. Now, my dear friends, this is graphical representation of this machine. This is graphical representation of this machine. Now, the same machine I will represent in the set form. The same machine I will represent in the set form. So, just we have discussed five different component of this machine, or five tuples of this machine. So out of these five tuples, four are set. So and one is initial state. So we will define it in set form now. Now I hope it is very much clear. So I will remove this from here and I will check it. Now see, this is graph form, graph representation of machine, graph form. Now in set form, the same machine can be represented as set form. Now you can see first set Q0, sorry, Q, capital Q. Capital Q is what? Set of all possible states of the machine. So in this machine, we have two states, Now you can see Q0, sorry, Q1, Q1, comma, Q2. So this is Q, only two states are there. Now, sigma is what? Set of all input symbols. So how many input symbols it is accepting? A and B, small a and small b. So I can write A, comma, B. Now third set is delta. Delta. Now, dear friend, how these transition rules are mentioned, that I will tell you. Now, how these transition rules are mentioned, That I will tell you. See, transition rule are specified as, in brackets, the present state, comma, comma, input symbol, current input symbol, and this is considered as pair, of q and pair of state and input symbol, and this gives us a new state, a new state, new state, right? Now, in the same way, if we are representing all these transitions, so you can see like this is format for one transition rule. So now Q0, sorry, Q1 we are having as, we are having one transition for Q1 and one transition for, one transition for A on Q1 and one transition for B on Q1. So on Q1, if we are getting A, then where we are moving Q1, we are getting A, then we are moving to Q2. This is first transition rule. Like second transition rule, on Q1 we are getting B, on Q1 we are getting B, and then we are moving to Q1 itself. We are staying on Q1. Now one more rule is there, Q2. On Q2 we are getting A, then we are staying on Q2. And for Q2, if we are getting B, then we are going back to Q1. So these are the four element of this set called transition function or transition set of transition rules, right? So this is sigma. So three component we have defined, q, sigma and delta. Sorry, this is delta. So three sets we have defined. Now Q0, in place of Q0, which is initial state, we are having here what? Q1. Q1 is an initial state that I have mentioned with this arrow. Now, set of final states. So F would be there as Q2, because Q2 is only final state in this particular machine. So remember, friends, Q, sigma, delta, and F all are set. So we need to enclose them in curly brackets. But Q0 is single state, so I have not included this in curly brackets. So this is single state, all these are sets. Although there is one member only in the set, but still we need to represent it as in the form of set. So this is how you can represent a DFA in set form. So if you are providing solution in the set form, or if you are providing in the solution in the graph form, then both are correct. You need to make either graph or the set. Both are correct in this way. So this is how you can create a DFA for particular language. Now there is one more representation of this particular transition set, and I will tell you what this representation is. So I hope if it is clear. So I'm reviewing this particular portion of this now. For DFA, you can see, friends, in all the rules we are having, for one combination of present state and input symbol, we are having only one choice, at the right hand side of each transition rule, only one choice we have. That means for each present state, each combination of present state and input symbol, there is only one choice. That means it is completely fixed, that for one combination only one next state is there. That means it is completely deterministic, and because of this it is called deterministic finite automata or deterministic finite state machine. Now one more representation for delta is in the form of Cartesian products. We are having, we can represent delta as transition function, which is written like this. So Q cross sigma gives Q. How we are writing it? You can see. In Cartesian product, again we represent members as pair of pairs. Um, uh, you can say pair, and you can say one member comes from first element of Cartesian product, and second member comes from second element of Cartesian product. And next is you can see Q cross sigma gives Q. That means one member from this set would be there, and one member from this set would be there in the ordered pair. In the ordered pair. So present state is belonging to Q, input symbol is belonging to sigma, and that is giving us one new state, which is again belonging to the set of all possible states, that is Q. So you can represent delta as Q cross sigma gives Q. This is another way of representing transition function. But this is only the definition of transition function. When you are creating machine for particular language, then you need to write all transition rules like this only, right? So I hope it would be very much clear. And if you have any doubt, you can always comment, and I will definitely reply your comments. Thank you so much. Thank you.